です。
はい、いきます。Good morning. Good morning. My name is Shuto Ota. I'm with Nagoya Institute of Technology, Japan. The title work design of discrete time binary controller using variable order data signal modulator. Let me explain the background of our work. The figure shows I diagram some control system with halogen heaters and solid state switch using AC power source. As a typical application, the electric harness can be cited. The background as follows. Recently, because of the demanded of high productivity and product performance enhancement, the control system needs to have rapid response. So, for heating process, halogen lamps are mainly used as heaters, since they have very short time constants. And the fire angle control is utilized since it has fine resource and rapid response. But now, harmonic problems of the power line has raised in many countries, and some treatments are required to use fire angle control. With the situation we have been proposed feeding power adjustment method which use the combination of the zero-cross switching control and the data signal modulation. Zero-cross control is a method of switching on/off when the AC voltage becomes zero. Using this method, precise adjustment can be performed with much fewer harmonic components of the consuming current. Next, I explain how to combine the crossing control and data signal modulation. However, this approach poses a problem when deciding data signal modulator. The data signal modulator has a trade-off relationship, operating range, and high noise reduction performance. When applied to a control system, for practical purpose, it is necessary condition to be able to operate over the entire operating range. However, this reduces the noise reduction performance. Therefore, the purpose of our work is to achieve both entire operating range and noise reduction performance. The approach is proposed a binary controller that satisfies both. Next, I will explain data signal modulation. This figure for the input signal is expressed by changing the pulse density, and in this block, this binary signal is used to switch the switch for temperature control. This figure shows is a technique that reduces the noise shaping. The quantizes noise in a specific frequency band by frequency shaping the quantization noise when converting analog signal to digital signal. The figure is the data signal modulator used in this work, and this noise shaping filter determines how the noise is shaped. We designed a noise shaping filter to reduce low frequency quantization noise, which is the frequency band of the plant. However, it is not just a matter of the design the filter to increase the noise reduction performance. For example, let's say that this low noise reduction filter can modulate an input signal from 1 minus A to A. At this time, this range is called the operating range, and the maximum voltage of the operating range is called the maximum modulation ratio. This higher the order of the noise shaping filter, the narrow A. If the signal exceeds the maximum modulation ratio, it will become unstable and will not recover. In this way, the sigma modulator has a trade between a wide operating range and high noise reduction performance. Here is an example of the operation of the delta sigma modulator. We use this noise shaping filter and input a sine wave as analog input. This figure is a comparison of the spectrum when only zero cross control is performed and when delta sigma modulation is combined with zero cross control. The horizontal axis represents frequency, and the vertical axis represents spectrum. As you can see from the spectrum, delta sigma modulation reduced noise in the low frequency region, reducing the effect of quantization noise in the low frequency signal band. In addition, it can be confirmed that increasing the order of the noise shaping filter also improves the low frequency noise reduction performance. Next, I will the approach in order to achieve both the inter-operating performance and high noise reduction performance. We tried the approach of a variable order delta sigma modulator. The proposed modulator dynamically switches the order of noise shaping filter. According to the input signal value, thereby enables operation in the entire operation range while maintaining a high noise reduction performance. However, the delta sigma modulator is delicate and may become unstable by switching filters, so it is necessary to ensure stability. Therefore, it is necessary to ensure the continuity of operation in addition to the input range. Two things have become devised for continuity of operation. One of them is the structure of the noise shaping filter. I will explain the filter structure in the proposed approach. One factor that causes instability when switching filters is that the internal state of the filter changes. Therefore, a filter structure that ensures continuity of state variables is considered suitable for filter switching. In this work, we attempt to secure stability by suppressing state change due to switching by making the noise shaping filter the following filter structure with only output coefficient. Also, these x1 to x3 are used as state stable. Parameter g0 to g2 can be calculated from this noise shaping filter of each other. When switching the order, for the first order, turn off here and here. For the second order, turn off here. For the third order, everything turn on. Next, I will explain the constraints on state variables during switching. In this work, we consider switching between first order and third order noise shaping filter. Here is a graph plotting the values of the state variables. The axis of this graph represents the state variables x1 to x3. We confirm that each filter has its own range of extents that the state variable can take. We call this region the stable region. It can be seen from the graph that third x1 has a more limited than the first order x1. Therefore, when switching to a filter with a high noise reduction performance, if the state variable is not within the stable region of the filter to which it is switched, it may cause instability. In this work, we have set the switching area. When switching from the first to the third order, the state variable x1 state switches after entering the switching area. Doing so ensures stability. Next, I will explain the order variable rule on the noise shaping filter. In selecting the orders, there are 4 constraint points. The first was order filter we used in the previous sample. The second is whether the input signal exceeds the modulation rate. The third is the hysteresis provided to prevent filter transition chatter. It has hysteresis gap and run count. The last one is the transition in the switching areas. Considering these, determine the order of the noise shaping filter at each sample. Simulation example as presented to demonstration effectiveness. Here is the temperature control system used for purification, and it is assumed that the heat source of the temperature control system is a halogen lamp with a short time constant. The control used an LQI controller and the sampling frequency used is 16 Hz. The controller calculates the power to supply to the heat source based on the feedback signal. The temperature of the object to be heated is controlled by converting the continuous value into 2 values with the data signal modulator that we propose on switching on/off. The data signal modulator's parameters and band used in the simulation are as follows. Next, we run the situation. The desired value is a step signal that rises from 0 to 0.45. The result is the 2 graph below. The graph shows the controlled value, manipulated value, desired value, and filter order. The left Looking at the graph, we can see that the order of the filter is dynamically switched according to the manipulated variable. This graph shows the power spectrum after the controlled value converges to the desired value. The proposed control method reduces noise in the low frequency band, confirming a high noise reduction performance. As can be seen from these 2 results, the proposed variable order data signal modulator enables both entering, operating range and high noise reduction performance, which were not possible with conventional data signal modulator. Finally, I will explain the summary of this work. The purpose is to achieve entire operating range and high noise reduction performance to the data signal modulator. The approach is proposal of the variable order the data signal modulator, and we confirm the both requirement for satisfied. Future work is evaluation with actual equipment. Thank you.